Hi everyone, we're going to start learning about the normal distribution today, which is chapter 3 in our year 2 book. So the normal distribution is a statistical distribution. You've learnt about some of these already. You learnt about general discrete random variables in year 12, and specifically you learnt about the binomial distribution. And the binomial distribution is an example of a discrete random variable. Discrete meaning, of course, that the data is countable and it can only take particular values. So, for instance, if you were to flip a coin 10 times and you might be interested in the number of tails that you get, we are talking about here a binomial distribution. So let x be the number of tails, and we wrote it like this. X is binomially distributed. If it's 10 flips, that means we have n is 10. The probability of getting a tail each time is 0.5. And if you remember, this fits a binomial distribution specifically because we had a fixed number of trials. Each trial was independent of each other, and the probability of success, in this case getting a tail, remained consistent from trial to trial. So the binomial distribution showed us what we could expect to happen and the probability of different values occurring. So we would expect, for instance, if we were throwing a coin 10 times, we wouldn't get many, and then we were counting the number of tails. The chances of us getting no tails at all is really slim. There is a chance, but very small. Chance of us getting one tail is a bit bigger, two tails a bit bigger still. And from the other end, this kind of mirrors quite symmetrically. So 10 tails, really slim. 9 tails out of 10, not quite so slim, but still very slim chance. 8 tails, very similar, same chance as getting 2 tails. Now, of course, the most likely occurrence is that we would get 5 tails, because we would expect really half of them to be heads and half to be tails generally. So our probability distribution and the chance of getting different values looks something like that. But this is a discrete variable. We couldn't get 1.5 tails, for instance, because that just wouldn't exist. Now, what we're going to focus on in year 13 is the concept of a continuous random variable. So it's the same principle as a discrete random variable, except the data we're dealing with is continuous data. And we know continuous data is something that can generally be measured. It can take any value within a range. So it might be something like height or weight, for instance. Those are continuous examples of continuous data. So, for instance, here we might say, let our continuous random variable x be the height of a year 13 student. Now, I'm going to assume that the average height of a year 13 student is about 170 centimetres here. So if that's the case, I would expect most students to be around that height. And as we get taller, the probability of a student getting being of a certain height is much smaller. So fewer and fewer students are we would find fewer and fewer students the taller we get, but similarly we would find fewer and fewer students the shorter we get. Now, not all continuous data fits this symmetrical shape, but what we're interested in today is specifically those data that do fit this symmetrical shape. And this kind of symmetrical bell-shaped curve that certain types of continuous data fit is called a normal distribution. So this shape here for continuous data is the one we're going to focus on. And normal distributions occur in all sorts of places. And lots of data tend to fit a normal distribution, either sometimes perfectly, but just like with anything in probability, generally they would kind of approximate a normal distribution and it will be close to that shape. But this distribution here has loads of important features, and that's what we're interested in. So there's a few things that I need you to be aware of before we even start, and that is on any continuous probability distribution like this, the area under the curve is always 1. And that's really important because that means that we can do lots of calculations and work out probabilities. And if we're talking about this being a probability distribution, the area must be 1, mustn't it? Because we know that the total probability of every possible option covered is going to be 1. So what kind of things are covered with a normal distribution? You might have things like heights of people in a population, like we've looked at here. You might have the weights of a population of animals. Errors in scientific measurements tend to be normally distributed, so the chance of the error being slightly away from the mean is very high, whereas as you get a bigger and bigger error either way in your measurements, that the chances of that happening reduce. So there's lots of things that fit a normal distribution, and it's really useful for us. Now, I've already mentioned this, a continuous random variable that's symmetrical about the mean, whatever the mean for the thing we're measuring is called a normal distribution. So this distribution, for instance, we can see is not symmetrical, the mean being this value here. So let's write mu for mean. This is not symmetrical. This is negatively skewed, meaning there are more, there's a kind of a bigger tail down this end. This one, so that's not normally distributed. This one is, there's the mean. We have a positive skew on this distribution, so that's not normally distributed. Whereas this one, there's the mean, and it's symmetrical either side, so this is a normal distribution. Now, the way we write a normal distribution, just like we did with our binomial, is we say that our variable x, and then we use the tilde sign, and the capital N this time. So that means x is normally distributed, and there are two parameters, bits of information that we have to give to help us define this. We write in the brackets the mean of this distribution, and we write the variance of the distribution. Now, you will remember that this sigma symbol stands for standard deviation. The variance is the square of the standard deviation, and that's the number that we put in the brackets here. Now, I jumped ahead of myself earlier on the video, and I was giving examples of normally distributed data. So we wrote down things like heights of, let's say, height of females in a population, for instance. I think the example in the textbook, one of the other ones it gives is, say, the weight of tigers in a jungle. Things like that tend to be normally distributed. Now, the normal distribution has certain features that we need to be aware of. I've already said that it's symmetrical about the mean. We've already talked about that one. I've mentioned the parameters, mu and sigma squared, so the mean, the population mean and the population variance. The idea between the symmetry in it, more specifically, is this, that the mean of the distribution and the median and the mode are all the same value. Now, we know we have a bell-shaped curve with asymptotes at either end, so let's make a note of that. Bell-shaped with asymptotes at either end. We have that the total area under the curve equals 1. And we also have some points of inflection on this curve. Let me get a different colour just to highlight this for you. So you've learnt about points of inflection in your pure maths. The point of inflection is where your curve turns from concave to convex or vice versa. And we talked about the idea of driving along the curve and thinking about when you would change the direction of the steering wheel. So your point of inflection is kind of roughly there and another one roughly there. Now, those points of inflection are at important places on this curve because if I just drop lines down here, that gap there is one standard deviation from the mean, and this gap here is also one standard deviation away from the mean. So whatever the standard deviation is for your particular data, you take your mean and you subtract the standard deviation to find where this point of inflection is. You then take the mean and you add the standard deviation to find where this point of inflection is. So let's make a note of that explicitly, and we have that the points of inflection are at the mean plus or minus one standard deviation. Now, the other thing that I want to point out here, and it's not something that you need to know as the main features, but it's a really useful bit of information, and that is that there are certain facts about the areas between the mean and the standard deviations that are very useful for you to know. So on this one here, I'm just going to highlight the mean, and I'm going to go to the points of inflection, there and there, and I know that that's 1 standard deviation away, so mu minus sigma, and this one is 1 standard deviation away, so mu plus sigma. And I'm interested now in this area here between those 2 points, because what we know about any normal distribution is that roughly 68% of the data lies within this area here, which we call 1 standard deviation from the mean. So what we say is that let's write it like this, 68% of the data lies within 1 standard deviation of the mean. We could write this more formally like this. We say that the probability that x is between mu minus sigma and mu plus sigma is approximately 0.68, like that. And there's another 1 or 2 facts that in a similar vein that are very useful for you to know. So the first one is, instead of going 1 standard deviation away, if I then go that same distance again, so about here, so that's mu minus 2 sigma, and then the same distance along here, mu plus 2 sigma, and my mu is in the middle there, that's 2 standard deviations from the mean. So that's this area here. And what we know about that area is that about 95% of the data lies within 2 standard deviations of the mean. So let's make a note of that one. The probability that x is between mu minus 2 sigma and mu plus 2 sigma is approximately 95%. And finally, there's one more which I won't draw for you, but in the same vein, if you go 3 standard deviations either side of the mean, you've nearly got the whole lot, because obviously by that point we're getting our asymptote's getting very, very close to the horizontal axis. So the probability that x is between mu minus 3 sigma and mu plus 3 sigma, that is about 99.7%, so 0.997. So that's some really useful bits of information that you need to know. These are all on pages 38 and 39 of your textbook. And make sure that you learn these features and you learn these values here as well, please. Now let's have a look at the first example from the textbook. Now in example 1, we are given a normal distribution curve, some normally distributed data, and it tells us that the diameters of a rivet that are produced by a particular machine in a factory they're modelled as a normal distribution. So let's make a note of the normal distribution we're told. We're told that these diameters, x, are normally distributed with a mean of 8 millimetres, a variance of 0.2 millimetres, so that's a standard deviation of 0.2 squared. I could here work out 0.2 squared, which is 0.04, but and so I could write 0.04 there, but I don't need to. I can just put 0.2 squared, and that's absolutely fine. So what we're saying here is that rivets are being produced in a factory. The average diameter of a rivet is 8 millimetres, and obviously they're aiming to have all of these being consistent, but the average deviation from this mean is 0.2 millimetres. So we would expect, going back to our data about 68% being within 1 standard deviation of the mean, we would expect that 68% of our rivets are between 7.8 and 8.2. And I'm going to come back to that in a minute because that's actually one of the questions here. So first of all, we are asked to give the probability that x is bigger than 8. So this is the way we approach a normal distribution question. We sketch the distribution itself, we mark on where the mean is, so in this case the mean is at 8, so we know that's in the centre of the distribution here, and we highlight the probability that we are asked for. So that's this probability here. So I need to point out this really explicitly, and that's that the probability is the area under the curve. And that's a really important principle for you to grasp when we're dealing with every question to do with normal distribution. Now, we said that the total area is 1, And we also said that this is symmetrical about the mean, which means we know that this area here is 0.5. So that means the probability that x is bigger than 8 is 0.5, or a 50% chance. And then we talked about, let's have a look at this one, sorry. We've got the probability that x is between 7.8 and 8.2. Now, I mentioned this briefly before, but in case you didn't quite catch what I was saying, these values here, 7.8 and 8.2, are both 0.2 away from 8. This one is 0.8 minus 0.2, this one is 8 plus 0.2. So what we're dealing with is this. There's 7.8, there's 8.2, and this is 1 standard deviation, and this is 1 standard deviation away from the mean. Which means that we know from our previous sheet that that area there is 0.68, because we know that 68% of the data values lie within 1 standard deviation of the mean on any normal distribution. So that's our example 1, and that gives you enough information to complete exercise 3A.